In biostatistics, there are some concepts that sound kind of abstract, but they're actually crucial if we want to trust the results we see. Today, we're going to break down one of the most important ones, degrees of freedom. So let's just dive right in.
Okay, so picture this. You hear about some amazing new drug. The first thing everyone, doctors, patients, you name it, is going to ask is, okay, but how sure are we that this thing actually works? And this isn't just some textbook question. We're talking about real-world consequences here.
So to make this idea really stick, let's use an example that, well, pretty much anyone can get their head around. We're going to imagine a clinical trial for a brand new headache medicine.
All right, so in our imaginary study, we've got 100 volunteers, all of whom get headaches, and they've all agreed to participate. This group of 100, that's our sample size, and we're going to be tracking the results very closely.
So what's the goal here? It's pretty straightforward. We want to measure the average improvement in their headache pain. We're going to boil everything down to a single number that tells us, hey, for this group, here's how well the drug worked.
But, and this is the big but, here's the million-dollar question. What if that improvement we saw was just a fluke, right? Just random chance, a statistical coincidence? How on earth do you separate a real effect from just random noise in the data? Well, that is exactly where this idea of degrees of freedom comes into play.
All right, section 1, why this concept matters. Let's start with the big picture. Why should you even care about this?
Okay, so at its heart, you can think of degrees of freedom as a kind of quality control check for our data. It's a tool that helps us figure out just how reliable our results are. It's what makes sure that when we say, hey, this drug works, we've got the solid statistical evidence to actually back that claim up.
Okay, section 2, what freedom means in stats. So what do we even mean by freedom here? It sounds a little weird, right? To get a feel for it, let's try a really simple analogy before we jump into the official definition.
Okay, check out this ice cream analogy. Imagine you've got 3 bowls of ice cream and 3 friends. The first friend walks up, they have 3 choices, right? Total freedom. Now the second friend comes along, their choice is a little more limited. They've only got 2 options left. But what about that last person? By the time they get there, their choice is already made for them. There's only 1 bowl left. There's no freedom at all. They get what's left. That idea, that one value is locked in, is what we call a constraint. And believe it or not, that simple ice cream example perfectly explains the real statistical definition. Degrees of freedom, it's just the number of values in a calculation that are actually free to be whatever they want. As soon as you add a constraint, like say you already know the average of all your numbers, well then that last value is no longer free. It's totally locked in. All right, section 3, the formula in practice. So let's get practical. How do we actually calculate this thing and, use it?
The good news is, for a lot of the most common tests out there, the formula is super simple. It's just df equals n minus 1. And yeah, df is just short for degrees of freedom.
Okay, let's plug in the numbers from our headache trial. So n is our sample size. That's the 100 patients. The -1 part, that's our constraint. Now, why is the average a constraint? Well, think about it. If you know the final average improvement score for all 100 people, and I give you the scores for 99 of them, you could actually figure out what that 100th person score has to be. It's not free to vary anymore. It's fixed. Just like that last bowl of ice cream.
So, for our clinical trial, the math is easy. 100 minus 1 gives us 99. So we have 99 degrees of freedom. And all that number, 99, really means is that once we pin down that overall average, 99 of our patients' results were still independent. They were still free.
But so what? What do we do with the number 99? Well, it's a critical piece of the puzzle. Statisticians plug this number into their calculations to figure out the strength of the evidence. It helps them answer that original question we had. Are these results real, or are they just a random fluke? And here's the key takeaway. The higher your degrees of freedom, generally, the more confident you can be in your results. Okay, so let's wrap this up with the key takeaways. First, degrees of freedom is basically the number of values that are free to vary. Second, it's an absolutely crucial tool for making sure research results are reliable. And third, for a lot of cases, the formula is as easy as it gets, just your sample size minus 1. All right, your next steps. And that is our quick and dirty breakdown of degrees of freedom. Hey, if you enjoyed this explainer, go ahead and like, comment, and subscribe to the channel. You can also listen to the audio version on Apple Podcasts. The link is right there in the description. We really do want to hear from you, so please let us know what topics you want us to tackle next. Our whole goal here is to make this stuff clear and accessible. Thanks so much for joining us.